to find the Laplace transform of ft equals sine at, and we could then write that as the Laplace of the function ft is equal to the integral, semi-infinite integral, which is going from 0 to infinity, e to power minus st times the function of ft dt, and that Laplace is called f of s. So you're converting the function of t to the function of s, which means you only see s in it plus constant. Now, because it's sine, I can write e to I theta is also written as cos theta plus I sine theta. This is the real part of a complex, and this is the imaginary part. So the imaginary part is what we need when we substitute the sine in terms of e to power I theta. If we get the real part, that will be for cos theta. So we can replace the function f of t with e to I theta, and the final answer will be the imaginary, which will be referring to sine theta. So what we can do is replace that with Laplace, and that would be, the f of t would be e I. Now the theta would be the a t, so that would be a t, and so that's what we want to substitute here, but we're looking for the imaginary part, so we could go for the 0 to infinity, which is what we call the semi-infinite integral, and e to power minus st times the e to power I a t dt. So what I could do is put imaginary here because that's what we want, but I want to do the integration so that I can get the cos as well. And I could now, we've done this integration before, but I will take this out. I would multiply the two exponential, and then we add the exponent because we have the same base. We add the power. 0 to infinity, e to power minus st plus I a t dt. So I'm going to take a common factor here, e to power minus s minus I a t. So I've taken minus t out as a common factor, dt. And if I integrate, we're going from 0 to infinity. If I integrate exponential function, I get the exponential function back and then divide that by the derivative of the exponent. What we're going to get next will be the square bracket here, e to power minus s minus I a t. So I get the exponential function back from this integration and divide that by the derivative of the exponent, which is minus open bracket s minus I a close bracket, and I'm going from 0 to infinity. So I can rewrite the Laplace as, well, take the denominator out because it's constant, so minus 1 over s minus I a e to power minus s minus I a t 0 to infinity. I'm going to replace t with infinity and t with 0 and then take away. But I can rewrite the first one of this by saying 1 over s minus I a. This will be 1 over e open bracket s minus I a, replacing the t with infinity minus e to power 0. If I replace it with 0, 0 times the exponent will be 0. If I replace t with infinity, I get e to power minus something infinity, which is what I've written down here in terms of indices. And as e to power infinity gets so large, 1 over e to power infinity will be 0. So we get minus 1 over s minus I a to bracket 0 minus 1. E to power 0 is 1. And if we simplify this any further, we get 1 over s minus IA. And so that will be the Laplace of e to the power iat. So what I need to do then is I'm looking at a complex denominator. I need to rationalize the denominator so that I can, because we don't want a complex in the denominator. So let's do that. We're still doing the Laplace of e I a t, and I need to rationalize the denominator. 1 over s minus ia times the conjugate of the denominator. The conjugate will be the plus, that is s plus ia over s plus ia. So I multiply both the numerator and denominator by the conjugate of the complex. That's the conjugate of that. The difference between the complex and its conjugate is a change in sign in front of the I. And that would be s plus ia over s times s will be s squared. S times ia will be sia minus ia times s will be minus sia. So that will cancel out. Minus ia times ia will be minus I squared a squared. I squared is minus 1. Minus 1 times minus is plus. So that will be plus a squared. And we can split this even further. So that will be s over s squared plus a squared plus I a over s squared plus a squared. So this is the real part and that's the imaginary part for the Laplace of e to the power iat. You got the real part and the imaginary part. So if we compare that with this, because that's for the I theta is iat, so I replace theta with at, so that would be at over there, at over there. So that means the Laplace of the imaginary sine theta will be a over s squared plus a squared. So let's write it out. The Laplace for sine at will be equal to a over s squared plus a squared, and the Laplace for the cos at will be s over s squared plus a squared. Now these can be done by using integration by parts, but this is much quicker. So you get the two of them in one go, and then you can isolate the real part and the imaginary part. So we could do the Laplace of sine 2t. Now we know that 2 is a is 2, so we have to put it there. So that will be 2 over s squared plus 4. So that will be the Laplace of sine 2t. What about the Laplace of cos 4t? We could do that too. The Laplace of cos 4t will be equal to, we can see that the a is 4, so it's going to be s over s squared plus 16.